How will the universe end? In this multi-part series, I'll explain one of the most likely and arguably the most likely scenario, heat death. In addition to how heat death can lead to the birth of a new universe, perhaps one precisely the same as ours. Don't worry, we'll get to that and much more throughout this entire series. In the future, I do intend on covering some alternate theories such as the Big Crunch, the Big Rip, vacuum decay, and the Big Bounce. For now though, let's focus on heat death. To understand all the complexities of heat death, there are quite a few mind-bending concepts that I'll set the stage with. For example, there comes a point in space so far away where the farther an object is, the larger it appears. Obviously, this contradicts our everyday experience. Something far away typically looks smaller. Well, there's a point where this actually begins to change. Don't worry, I'll explain all that and much more in this multi-part series. 1915, Albert Einstein publishes his equations of general relativity without the cosmological constant. Comes 1917, he adds the cosmological constant when he realizes that his theory was implying that the universe was dynamic, where space was a function of time. At the time, Einstein and many others believed that the universe was static. This parameter fixed that. 1927, Georges Lemaitre, a Belgian astrophysicist, illustrated that the universe is actually expanding by combining general relativity with some of Hubble's recent findings. Comes 1931, Einstein accepts the theory of the universe expanding, calling the cosmological constant one of the biggest mistakes of his life, right next to the letter he sent to Roosevelt, neither of which I blame Einstein for. You see, in both cases, Einstein had his heart in the right place. You see, in 1917, the Big Bang theory wasn't yet widely accepted. This was well before Hubble's findings regarding the expanding universe, as was the discovery of the cosmic background radiation. A steady-state universe was still arguable. If you want to know more about this battle of the theories and what came before the Big Bang, feel free to watch this video a little bit later. Since Einstein did not know the universe was expanding, he needed to add the cosmological constant to prevent the universe from collapsing due to gravity. He figured that all the stars in the night sky would be slowing and attracting one another, drawing closer and closer. Despite nothing in the universe being able to counteract gravity, perhaps space itself could, hence where the cosmological constant derives from, to fix this hypothetical problem. The equation worked. Only one problem was that it only worked for a static universe, which we know is not the case. The universe is expanding. In fact, the rate at which it is expanding is even accelerating. This became evident when Hubble used the red shifting of those galaxies to show the universe was expanding. Hence, if the universe was expanding, the cosmological constant was no longer needed. The universe could instead be saved by the simple fact that the expansion countered gravity, even if that gravity eventually caused the expansion to slow, stop, and reverse course. Again though, this does not seem likely, given that the expansion rate is in fact accelerating, making the Big Crunch theory of the end of the universe rather unlikely. While at the time Einstein was embarrassed by the cosmological constant, comes 1998, he actually may have been partially right to include it. The Supernova Cosmology project illustrated that the expansion rate was in fact not slowing down, but rather accelerating due to the cosmological constant, that of which may represent 70% of the total mass energy density of the universe. The High-Z supernova search team announced that they had found the same results in their data. But just because the cosmological constant works doesn't mean it's considered to be a rational solution. Nothing really explains why it should have the value it does. Why does it exist at all, aside from fixing the equations? Well, if you saw my prior video, you might be thinking, maybe it's quantum fluctuations. Well, this actually can't be the case. The calculations required for quantum field theory to be the case would lead to an order of magnitude 120 orders larger than what the cosmological constant actually gives, which is huge. Hence, generally, any hypothesized phenomenon that could provoke an acceleration in expansion is now referred to as dark energy. We know that whatever initially caused cosmic inflation eventually turned off, but this dark energy that allows the universe to continue expanding and now once again actually accelerating in its expansion is still there. Well, why wasn't dark energy always causing the universe to rapidly expand? Well, as cosmic inflation was beginning, there wasn't much space between all the matter. Everything was very, very dense, making dark energy have a lower effect. As the universe continued to expand, dark energy was able to have more of a notable effect since there was more space in between all the matter. It's a positive feedback loop, as you can see. The more the universe expands due to dark energy, the more the universe will continue to accelerate in the rate of expansion. It was about 6 billion years ago that matter got so diffused due to order ordinary cosmic inflation that the effects of the cosmological constant, or dark energy, became very noticeable. So I made a chart to illustrate this and hopefully give you a better understanding. Shut up, I'm not an artist, alright? But as you can see, eventually the exponential acceleration becomes very clear, resulting in a probable heat death, where max entropy would then be eventually reached, thus the concept of time would eventually cease to exist, since there would be no matter to bend space-time, leaving something very, very interesting to potentially occur. But to be continued in this multi-part series. You shall see what that something is, and it might just blow your mind. Anyway, as Katie Mack explains in The End of Everything, we can now measure the motion of supernova explosions so far away that they went off before the expansion began to speed up 6 billion years ago, meaning that we can trace out when the universe was decelerating and pretty much when it transitioned to acceleration. Dark energy still might not be some new dynamic field, but so far, a cosmological constant fits the data perfectly. Ironically, when Einstein initially created the cosmological constant to save the universe from collapse, it actually might be what leads to our doom, but rather than by collapse, through heat death expansion. Make sure to subscribe and enable post notifications, this way you don't miss the next episode of this mind-bending series where I describe the most probable way the universe not only ends, but potentially restarts, perhaps even exactly the same way it is right now. Now, before moving on, just wanted to mention that eDeals is now open for a finite period. You can purchase a membership with the link in the description for only $14.99. All information regarding it can be found on the eDeals website, again, linked in the description. It's an excellent way to help you guys save hundreds of dollars every single month through free food, heavily discounted orders, free Amazon products, in addition to monitors and release info as well, and much more. Again, the link is in the description below, so feel free to join. An apocalypse caused by dark energy is a slow and agonizing one. Isolation, loneliness, and emptiness, a slow fade to black. The cosmological constant doesn't quite end the universe, rather, it ends everything within it. Once it begins, the accelerated expansion never ends. How will the universe end? In this multi-part series, I'll explain one of the most likely and arguably the most likely scenario, heat death, in addition to how heat death can lead to the birth of a new universe, perhaps one precisely the same as ours. Don't worry, we'll get to all that and much more throughout this series. To understand all the complexities of heat death, there are quite a few mind-bending concepts that I'll set the stage with. Last episode, I explained why the universe is not only expanding, but actually accelerating in its rate of expansion. Well, today's topic is even more insane, a topic that contradicts reality as you know it. The vast observable universe as you know it is in fact bigger than you think. That observable part that refers to the area within our particle horizon. This is the farthest we could possibly see with our most advanced instruments. This is due to the limitations of the speed of light as well as the actual age of the universe. While extremely fast, light of course does take time to travel. Therefore, from our point of view, farther objects are also farther in the past. Hence, there also must be a distance that corresponds with the beginning of time itself. Some distance where if light started there at the very first instant, it would take the entire age of the universe to reach us. This is what defines the particle horizon. It is the farthest we could observe anything. Given that the universe is 13.8 billion years old, you might think that this means the particle horizon must be a sphere of radius 13.8 billion light years. However, that would only be under the assumption that the universe was static. As we've already established in the prior episode, as well as this video, present-day evidence suggests that the universe is dynamic. It is in fact expanding and accelerating in expansion. Throughout the entire age of the universe, it has been expanding, whether it was the cosmic inflation at one point causing the majority, and it then passing the ball on to dark energy 6 billion years ago to continue, it's been expanding this entire time nonetheless. Therefore, something close enough to send its light to us 13.8 billion years ago is now over 45 billion light years away due to expansion. Hence, the observable universe can be considered as a sphere of about 45 billion light years in radius centered on on us. The closest we could get to actually seeing this edge is the cosmic microwave background, that of which you might recall from this video right here. It played a key role in verifying the claims of the Big Bang Theory when it was first discovered. But here's where things get really mind-blowing. We could also see galaxies which are now over 30 billion light years away, much closer than the edge of the particle horizon. Now, the light from those galaxies began traveling towards us long before the galaxies themselves reached such vast distances. If this was not the case, the light coming from them would not have sufficient time to reach us. You see, since our universe is expanding and accelerating in expansion, more distant objects are receding more quickly. Hence, there is a distance where the speed of the object, such as a galaxy, is moving away faster than the speed of light. In other words, the speed of light can't quite catch up with the speed at which the object is moving away from us. Now, hold on. I know what you're thinking. Nothing can move faster than light, right? Yes, that is true, but there is no limit to which objects in space can happen to find themselves farther apart, since they too are sitting in space, which is getting bigger and bigger in between them. It is the expansion of space itself in between which is faster than light, not the galaxy moving away. The discrepancy between this speed of expansion of space between objects is actually pretty close to the speed of light. Nonetheless, it is still faster than the speed of light. Okay, so how are we even able to see objects in space that are so far away that have been receding away faster than the speed of light? Well, you see, the light left the source of the object, such as a galaxy, very, very long ago, before the many years of expansion. It left this source so long ago that the universe was significantly smaller and thus had less distance to cover, despite the continuing expansion. Hence, eventually it was able to catch up, for lack of a better word. As the expansion slowed, it reached a part of the universe that was so close that the recession speed was then less than the speed of light. It entered our Hubble radius from the outside, as Mack, the author of The End of Everything, puts it. Confused? Don't worry, here's a very simple analogy to help you better understand this. Imagine you are standing on a huge treadmill that is moving faster than the speed you could run at your top speed. Despite running at your best top speed, you will still be moving backwards little by little. However, if you manage to stay fast enough where you don't quite fall off the treadmill, perhaps the treadmill begins to slow down due to a bad motor, then you could finally catch up to the front again. And then finally, as you see in the last image here, despite initially falling behind, as the treadmill slows down, you could finally catch up and reach your destination. So, hypothetically, if you were in a universe whose expansion is slowing down, you'll be able to see more and more distant objects as time goes on. Well, that's cool and all, but unfortunately, that's not our universe. Dark energy ruins all the fun since our expansion is accelerating, not slowing down. For the past 6 billion years, it's been accelerating in expansion ever since cosmic inflation handed the ball off to dark energy, as you might recall from the chart in the prior episode. So, while the Hubble radius is actually growing in size, it's not growing fast enough. In fact, it's growing so slowly that we're actually losing visible objects that we once could see before, and as it grows, we don't see anything new. We're only getting back what we lost due to the expansion. In fact, eventually, no galaxies aside from just one of them will be visible. The only one that will be visible is the one that is moving towards us, since it's close enough where gravity is strong enough to counter the expansion. That is Andromeda. The same galaxy will have collided with our own. If you notice, Andromeda is a different color than the many other galaxies out there. This is due to redshifting, something perhaps I'll make a full video on. But wait, things get even stranger. Remember, I said there comes a point in space where the farther an object is, the larger it will actually appear, contradicting reality as we know it? Well, here we go. For a very long distance in space, things do indeed appear smaller the farther they are away from us. However, there does come a point where this relationship reverses. This is great for astronomers because it allows them to easily view very, very far objects, since they appear larger than they actually are. Now, the reason for this reversal is similar to the reason why we could see things that are moving away from us faster than light. In the past, when the light emitted from them, they were much closer to us. Despite them being much farther away currently, the light they sent us has been already traveling all this time, and it's just reaching us now, showing us an image of something that used to be much closer than it actually is in reality. The farther back in time you go, the smaller the universe was, meaning less distance to travel. Now, this is certainly fascinating, the fact that it seems to contradict reality as we know it. Unfortunately, though, this means very, very bad news for the future of the universe, that of which we'll be exploring in the next episode. So make sure you do subscribe and enable post notifications, this way you don't miss out on it. Anyway, I hope you guys found this intriguing. If so, feel free to share it with a friend, especially if they're drunk. I promise the look on their face will be priceless. Feel free to leave a like if you enjoyed, or perhaps if you learned a thing or two. I'll leave the link for The End of Everything by Mack in the description for those interested in reading it. I do highly suggest it. With that said though, have a fantastic rest of your day, stay skeptical, stay curious, and until next time. Dark energy, why must you be so cruel? What is now visible in our Hubble radius will one day become lost in darkness due to the accelerated expansion of dark energy. Just like an ancient photograph slowly deteriorating, galaxies whose distant past is now visible will soon fade to darkness. Following the collision of the Milky Way and Andromeda, even our local group of galaxies will one day become invisible. We will be isolated, alone, surrounded by nothing but darkness. But this is merely the beginning of the end. How will the universe end? In this multi-part series, I explain one of the most likely and arguably the most likely scenario, heat death, in addition to how heat death can lead to the birth of a new universe, perhaps one precisely the same as ours. Don't worry, we'll get to that and much more throughout this series. To understand all the complexities of heat death, there are quite a few mind-bending concepts that I've started to set the stage with. Over the prior episodes, I explained why the universe is not only expanding, but actually accelerating in its rate of expansion. Consequently, distant galaxies have now started to disappear. Unfortunately, today's topic is the darkest of them all. Eventually, each new dying supergalaxy will be utterly alone. Nothing will again approach to bring in a fresh supply of gas to fuel new stars. The stars already shining will soon burn out, exploding as supernova, or more often, their outer layers becoming slow-burning relics, gradually cooling for billions or trillions of years. Black holes will grow for a time. Some will engulf galaxies worth of dead stellar remnants. Some will stall in growth, with no new matter approaching close enough to be consumed. When the stars have all faded to darkness, the ultimate decay sets in, as Mack, the author of End of Everything, explains. And it is here that, yes, even black holes begin to evaporate. Initially, most believed that black holes were eternal. However, in the 1970s, Stephen Hawking calculated that the quantum effects of black holes' horizons causes it to glow. This glow inevitably requires energy from the black hole. This then causes the black hole to lose mass. The process begins slowly, but becomes faster and faster until an explosion and disappearance at the very end of the black hole's extremely long life. Yes, even these massive black holes at the center of galaxies will also eventually fade to darkness. Of course, the same matter that makes up planets and stars will also fade to darkness. If any type of matter is left long enough for a long duration of time, it too will decay, since the majority of particles of matter are unstable. For example, a neutron will decay into a proton, an electron, and also an antineutrino. It is also estimated that this would take over 10 to the power of 33 years. After that long of a period, even hydrogen atoms, the most abundant atoms in the entire universe, will also decay. The culprit behind this agonizing fade to complete darkness is dark energy. However, this slow fade to darkness merely is the beginning of the end. The term heat death might be misleading, considering the end is actually much cooler and darker. However, in this case, heat actually refers to disordered motion of particles. If you watch my video on distinguishing the past and the future, you'll know precisely what I'm heading towards, and that is entropy. Entropy is explained in terms of how disordered something is from its initial state. To give you an example of this, a completed puzzle has low entropy because there is only one particular way it could be constructed as a whole. However, a pile of the puzzle pieces can be in any amount of configurations and still be considered a pile of pieces. It's not quite this simple though, and I'll come back to this example to explain why later. Additionally, entropy is linked to a higher temperature. For example, a block of ice has molecules arranged in a very particular order. A liquid, on the other hand, allows them to move much more freely. Water also happens to be warmer than ice, of course. The same idea applies to steam if you take this one step further. Most notable takeaway here is that according to the second law of thermodynamics, entropy can only increase in an isolated system. This can never be reversed. If you recall from this video, you'll know that it is precisely this process that allows the past to be distinguished from the future. Eventually, if you leave something long enough, it will decay into disorder. Now, I know what you're thinking. Can't you just put the pieces of that puzzle together and reverse entropy? Did you just break the laws of thermodynamics? Well, unfortunately, no. While you did decrease the entropy of that specific system, being the puzzle, that does not account for what is outside of that particular system. Oh, right, the rest of the universe. When you spent time putting it back together, your body was using energy from your digested food, your fingers gripping the pieces was causing friction, and even you breathing was causing more entropy as well. So, unfortunately, no, you can't break the second law of thermodynamics when considering the entire universe as a whole system. Now, I know what some of you really smart folks might be thinking. Aha, well, what if I throw myself into a black hole after finishing the puzzle? Not even light could escape a black hole, so does that mean you've effectively reduced the entropy of the puzzle and got rid of the evidence, aka increased entropy, by throwing yourself into a black hole? Well, if you choose to do that, best of luck to you. Unfortunately, your death will all be in vain. Black holes, too, have their own entropy. When you throw yourself into a black hole, its mass will increase proportionally to the size of you, which increases the horizon size and thus the surface area of the black hole where energy is emitted through Hawking radiation. And this all leads to the conclusion that yes, even black holes will also evaporate away, no matter how long it takes. All they leave behind is some radiation spreading out through an extremely dark universe, accelerating an expansion due to dark energy. In other words, eventually everything will fade to complete darkness. Not even black holes will survive heat death. Now, while this end is very dark, agonizing, and perhaps disappointing, this means that a maximum entropy level will eventually be reached. And now what this means for the concept of time itself is truly remarkable. Because of this, it leads to something quite spectacular. In fact, it's so insane that you might not be able to wrap your mind around it. By insane, I mean in the next video, we'll be discussing why it's completely reasonable to believe that our universe will be recreated precisely as it is right now, with you watching the video right now and perhaps even subscribing. A universe whose future is plagued by the acceleration of dark matter, the cosmological constant, is inevitably evolving towards a future of emptiness and darkness. As the rate of expansion continues to accelerate, there's more and more empty space and thus more dark energy, an unstoppable positive feedback loop. Eventually, all stars will have burned up, black holes will have decayed like everything else, and only exponentially expanding space will remain. This is de Sitter space. Given this ever-expanding space, does that mean the universe truly ends? To answer this question, we must venture into the depths of entropy and the arrow of time. How will the universe end? In this multi-part series, I explain one of the most likely and arguably the most likely scenario, heat death. In addition to how heat death can lead to the birth of a new universe, perhaps one precisely the same as ours. Don't worry, we'll get to that and much more throughout this series. To understand all the complexities of heat death, there are quite a few mind-bending concepts that I've set the stage with. Over the prior episodes, I explained why the universe is not only expanding, but accelerating in the rate of expansion. Consequently, distant galaxies have now started to disappear, as well as why this process is irreversible. This is the final episode of How Will the Universe End? Whenever a star burns out, a particle decays, or even a black hole evaporates, matter is converted into free radiation. This free radiation spreads through the universe as heat, pure, disordered energy. When something is reduced to heat radiation, its entropy is thus increased to the maximum, since there are no longer any restrictions on the flow of energy. Now, as the universe continues to expand, you might assume that this radiation becomes diluted, and perhaps the entropy should consequently drop as temperature does, but this does not occur. As Mack, the author of The End of Everything, explains, When the universe reaches a state of steady exponential expansion, you could define a radius from wherever you are, beyond which the rest of the cosmos is forever hidden. It's a true horizon in the sense that nothing beyond it could ever reach you. It turns out that this horizon, like a black hole's horizon, also has entropy associated with it, and thus a temperature. The difference is that instead of the heat going out, like it does with a black hole, it goes in. The temperature is very small, something like 10 to the power of negative 40 degrees above absolute zero. But when everything else has decayed, this radiation is all that is left to contain all the entropy of the universe. When the universe gets to this pure de Sitter state, it is a maximum entropy universe. From that point on, there is no way for the universe's total energy to increase, which means, in a very real sense, the arrow of time is gone. If you recall from the last episode, or even this video right here, the arrow of time and the second law of thermodynamics is absolutely essential to the functioning of the universe. If there is no longer a way for entropy to increase, consequently, it is no longer possible for any organized structures or any form of evolution to exist at all. Energy moving from one place to another is required for anything to really happen at all. Energy gradients are the basis of everything that performs some kind of work, and they can no longer exist in a universe which is essentially just a huge, very cold heat bath. But there are some exceptions, and these exceptions are not minor. In fact, they change everything. When it comes to the quantum scale, or even large scales, if you wait long enough, and by long, I really mean very, very long, not the kind some men will describe one of their organs as. If you wait long enough, unpredictable fluctuations will spontaneously shift some parts of the system into a low entropy state at random. Now, if you saw this video, you might already know where I'm heading with this. But anyway, the larger the system is, the less likely it is that fluctuations can do anything at all. However, when it comes to a universe that is eternally accelerating in expansion and contains only a cosmological constant, there is certainly a lot of time and space for something to occur, no matter how extremely rare it is. If there is a probability for something, no matter how vastly low that probability is, it will occur given infinite time. In fact, it will occur an infinite amount of times. It is extremely unlikely that a full-built piano will randomly spawn in empty space, but with infinite time, in principle, it can happen. Well, if anything can spontaneously pop into existence due to these fluctuations, then a universe very well can too. And again, in principle, given infinite time, technically, it has to eventually occur, no matter how long it takes. In statistical mechanics, there's a principle that states that any arrangement of particles in a system will eventually find itself in that same position once again. The less likely that configuration, though, the longer it will take. This is called the Pyeongcha Recurrence. Thus, if you have an infinite amount of time to work with, any state can be in is a state that it will be in again for an infinite amount of times. The reoccurrence time would be determined by how rare that occurrence is. For example, physicists Anthony Aguirre, Sean Carroll, and Matthew Johnson calculated that if you were to wait around 1 trillion times the age of the universe, a very long time, you could watch an entire piano randomly assemble itself in an empty box. Post-heat death universe is essentially just one giant box for all these random fluctuations to occur with infinite time. If the Big Bang is a state the universe has been in once, and the post-heat death universe is eternal, aka infinite time, then it not only can, but will occur again an infinite amount of times. With that said, this moment, right now, as you are watching this video, still not subscribed, without any notifications on, can occur exactly as everything is an infinite amount of times. I'm sure a lot of you guys have heard the Big Bounce theory. Well, this is unlikely to occur. Perhaps I'll make a video explaining why. Same goes for the Big Crunch, but that does not mean that the universe cannot be born again. It's just a different way, and it is this way, through heat death and random fluctuations over infinite time, that it is actually extremely realistic. For all we know, this may not be the first universe. Something very interesting to ponder is, can your precise consciousness be recreated, and thus, you could live again through this? Or, alternatively, do you believe it would be similar to uploading your consciousness to a computer, essentially making a copy while you still die forever? I have no idea, but I'd like to explore this in a philosophy video one day, and we'll come back to this later. In fact, Nietzsche was known for considering this possibility before he even knew that this was actually physically possible, before the concept of heat death was known to anybody. One of our most famous philosophers might have actually gotten it right. Now wait, it gets even more insane. According to this, it's actually extremely more likely that your exact brain, with all of its memories and abilities, can spontaneously appear in a closed, safe environment in random space where it can imagine this precise scenario, since even lower entropy would be required for the entire Big Bang compared to this. So according to probability, it is more likely that we live in a simulation. Personally, I was never a big fan of the simulation theory, but whenever that simulation theory is spoken about, it's rarely ever explained in this manner. Rather, it's explained in terms of some intentionally created program, which I feel is stupid since there have never been any recorded glitches. This, however, is the Boltzmann brain problem, and it's actually quite reasonable. However, I personally disagree with this, as do many physicists and cosmologists. Despite the lower change of entropy required for it, it still might be much more likely for a Big Bang to occur, and I'll explain why that is. Some cosmologists argue that it is much more likely for a de Sitter universe to create a low entropy state like the Big Bang, rather than something small on the brink of reabsorption. The argument here is that recreating a low entropy state might seem to require a lot of quantum fluctuation energy, but actually takes out only a little bit of total entropy from the system as a whole. However, other cosmologists still disagree with this, so we may never truly know if this is a simulation or not. Personally, I'm on the side that it is more likely for a low entropy state such as the Big Bang to reoccur, but what does my opinion matter? I'd like to hear your opinions in the comments down below. Under the assumption that this perspective is indeed accurate, my biggest question still remains. When the universe is recreated through the same exact Big Bang an infinite amount of times, is our own consciousness also perfectly recreated, or will it just be a copy? In other words, can we live again, our exact same lives without even knowing it? Or will it just be a copy, like uploading your consciousness to a computer? No matter which is the case, I do find something very special in this possibility, and that is hope. Hope that perhaps we could live again, and perhaps we already have, an infinite amount of times without even knowing it. Just the fact that this is a physical possibility gives me hope, and if I have to live this same life again, an infinite amount of times, you bet I'm going to live my best possible life, and I hope you guys do too. Ladies and gentlemen, this has been How the Universe Ends and perhaps Restarts. Subscribe and enable post notifications for more.